Right. So we continue with our idea of osmotic pressure, and we now look at one of the main applications of osmotic pressure, which is determining the molar mass of something using measurements made of pressure or the effect of dissolving something in a substance, measuring the pressure exerted by dissolving this substance. So when you dissolve something in a liquid, there will be some pressure exerted by the liquid on, for example, if you connect a manometer to that liquid, it's going to exert a pressure. Measure that pressure at a certain temperature. You know what the volume of the solution is, and hence you'll be able to determine the molar mass of the thing that you dissolve, and because you know how much of it that you dissolve. It's a very useful kind of tool. So let's say, for example, you have this situation where you're dissolving a bacterial gene fragment and you dissolve a certain mass of it and enough water to make a specific volume of solution. We're told the pressure that we measure, so in other words, the osmotic pressure that we then measure, is 3.4 torr at a specific temperature. What is the molar mass of the gene fragment? Right. So we start by writing our osmotic pressure equation. It is CRT. Osmotic pressure is equal to CRT. And of course, C is N over V. So if we get N, then we can get the molar mass. C is N over V multiplied by RT. So whenever you need to get the molar mass from the osmotic pressure, you know you need to get C is N over V, and then you can go from there. So in this case, let's call it N bacteria fragment, the number of mole of bacteria fragment is equal to the osmotic pressure multiplied by the volume over RT. And honestly speaking, you can plug in the pressure, you can plug in the volume, make sure that your R has units of liter and torr, and your T is 298.15 Kelvin, and you should get a value of 5.759 times 10 to the power minus 6 mole. Now, of course, there's numbers here. Okay, that then means that our molar mass of our bacteria fragment is equal to the mass, which is 17.6 times 10 to the negative 3 gram, divided by the number of moles. So 5.75 times 10 to the negative 6 mole equal to, rounded, 3 significant figures. Yes, 3 significant figures. So it gives us 3060 gram per mole. 3 significant figures. Why? 25.0, 3.40, 17.6, 31.5. All of them are 3 significant figures. Okay. It's a little dot here. Okay, so that's the molar mass. All right. Normal application of osmotic pressure. Next question. If the solution density is a certain value, how large is the freezing point depression of the solution? Now, this one might seem a bit interesting. So we first discuss how do we normally calculate freezing point depression. So let's just start there. We would say, well, the change in freezing point is going to be equal to KFP times the molality of the solute. The solute in this case is the bacteria fragment. And of course, we make up here with water. So what is KFP? KFP has something to do with our solvent. So it has to do with the solvent. Luckily, nothing with the bacteria, so we don't have to really concern ourselves with that. So we know stuff about water. That's something we can look up in a table. And we know how much we dissolved, and we know how much water we use to dissolve that. Because what is molality? Molality is mole solute per mass solvent. So we can actually calculate the change in freezing point. Right. So it's not as shocking as you might have thought. So what we're looking for is we're looking for the mass of the bacteria fragment. And actually we have the mass of the bacteria fragment. What we're looking for is we're looking for the mass of the water. And the mass of the water is of course equal to the 31.5 milliliter. And we know what the density is. It's 99.7 gram point milliliter. It's 31.40 gram. This is not the mass of the water, it's the mass of the solution. That's why I confuse myself. So the mass of the solution is that. Then the mass of the water is 31.40 minus 0.0176, because that's how much bacteria we dissolve. Yes. Which gives us about 0.0313 and so forth kilogram water. Okay. I mean, you should, it's just a different way of telling you the mass of the water. And because in this case, it's clear that the reason why the density is given is because you can't assume that the density of water is 1 gram per milliliter in this case. Otherwise, it would have been exactly 0.0315 kilogram. But you see, it's 0.0313. Okay, kilogram water. So now we have the mass of the solid, we have the mass of the water, we have the number of moles of the bacteria fragment. We calculated that earlier. We have the mass of the water, so we can calculate the molality of the solute. So M solute, and again, you're more than welcome if it works for you to use something like MCM solute, as long as you define it to say that I'm going to use this symbol for solute is equal to that for the bacteria fragment, the number of moles of the bacteria fragment divided by the mass of the water. And you should find a value of 1.83 times 10 to the minus 5. And when you calculate molality, the unit is molar, or it is mole per kilogram. But mole what? Mole solute per kilogram solvent. And so we calculate the change in the freezing point. You look up the constant for water, that's minus 1.86 degrees Celsius, kilogram per mole, which is, of course, a hidden way of saying per molar. And you multiply that by this 1.83 times 10 to the negative 5 molar. You should get a value of minus 3.41 times 10 to the negative 5 degrees Celsius. Question asks, well, how large is the freezing point depression? So that's where you stop. That is how large the freezing point depression is. It's not very large. It's quite very small. I mean, 10 to the minus 5 is a very small number. It's very small, the freezing point depression. And basically, the point of this was actually just to remind you that this KFP, for any freezing point depression or boiling point increase or whatever, it's that constant is connected to the solvent. The molality is connected to the solute. But in any case, yeah, that is it for this example. I'll see you in the next one.